The serious clinical complications of infections have motivated biomaterial scientists and engineers to explore novel ways in order to assist our colleagues in healthcare whenever implant materials and devices are involved. In Lecture 22, we'll review a case study regarding bacteria. This case illustrates the development of new ideas in designing and formulating and exploring new biocompatible materials which prevent the bacteria interactions, formation of a biofilm, and therefore prevent and or minimize subsequent infections. An interesting biomimetic approach was reported in the popular press a few years ago. A company in the United States was inspired by sharks. These are fish which live for 20 to 30 years. And very interesting detail is the fact that their skin is very smooth and it never promotes the attachment of, or growth of either algae or other calcium-containing deposits. Growth of algae and calcium-containing deposits have been reported on the skin of whales. These are again mammals which live in the sea and survive for many, many years. The contrast between the two types of animals was something that attracted the attention of this particular company, and what they did was to look at the skin of the sharks all the way down to a great detail. When they looked at the skin of the sharks under some great magnification, of course, using the high-power microscopes, they noticed the arrangement which is shown on this particular frame. The researchers in that company tried to mimic this particular pattern by putting on a flat surface these patterns with the linear segments which have a big center part and then on each side 2 or 3 others of diminishing length or height. The name of the company is called Sharklet Technology. They used these particular new formulations, and of course we don't have great details because they consider those aspects as the secrets of their company. That is not atypical of what companies do when they develop a new product. They use this particular pattern on surfaces of materials which they then expose to various pathogenic microorganisms. According to the report, they use different types of microorganisms like Staphylococcus aureus, Pseudomonas, and others are shown at the bottom of this particular slide. The interesting thing here is to see and compare the growth of these microorganisms on the same, chemically speaking, material when the surface is smooth, and this is the top row of this on this slide, and compare the results on samples of their modified, topographically modified surface. Those results are shown on the lower row of micrographs. Let us consider what happened when the pathogenic microorganisms were allowed to interact with the smooth surface. You see at the beginning a few, maybe only one pathogen adhering on the surface, but the number of the adhering microorganisms as a result, of course, of their proliferation increases during day 2. They start making colonies by day 7, and definitely by day 14 they are big colonies, and I'm sure that if the particular growth was checked out, perhaps they had a biofilm on the top which protected this particular colony. Let us now compare what happened on the topographically modified surface of this new product. On day 0, I personally cannot see any, or maybe there's some, but very few pathogens adhering. But by day 2, you may see 1 or 2. Few more pathogens adhere on the micropattern surface at day 7, but even by day 14, the number of pathogens adhering is much smaller on the micropatterned surface versus the smooth surface of that substrate. And definitely on day 14, there's no growth of any colony of any size on this particular novel substrates. It is obvious that the desirable outcome which was obtained by this new formulation of a material substrate was prevention of bacteria adhesion. The justification and rationale is that when the microbes, pathogens, are prevented from adhering on a surface, if something disturbs or inhibits that particular interaction and subsequent colony formation, this is a desirable outcome towards prevention of bacterial adhesion, because if these pathogens do not adhere on the surface, they are not going to survive, and therefore that particular approach becomes an interesting strategy for preventing infection-related complications on material substrates. We should also mention that in addition to preventing the adhesion and therefore the survival of pathogenic microorganisms on substrates, other desirable outcomes is, of course, the formation of the biofilm. Once that biofilm is formed, the colonies of the pathogenic microorganisms are very nicely protected, and they cannot be defeated or killed by either the immune defense system of the body or by various medications such as antibiotics, which are prescribed to patients who are suffering from these infection complications. The justification and rationale, therefore, for the other desirable outcome is to prevent the formation of the biofilm, therefore eliminate the protection of the enclosed bacteria, which of course they enjoy under the protection of the biofilm against the drugs, against the host immune system. As a result, the pathogen microorganism can be targeted successfully for extinction, for elimination. Moreover, clinical complications which are related to infection may be avoided. The requirement to prevent infection related to implantable materials and devices has now to be added on the list of the other desirable outcomes which we have been discussing in this course so far, namely that what we are aspiring is to and hope to to have as an outcome is timely and uncomplicated resolution of the wound healing process around the implantable materials and devices, and formation of normal, functional new tissue. This is the combination now of the requirements of the most desirable outcome pertinent to implantable materials and devices. Ways to achieve this particular desirable outcome now require the design and production of what we call bifunctional material substrates. Please make sure that this particular term, bifunctional, is not confused with biofunctional. Bifunctional means that this particular substrate now has two very important characteristics. An example will be to put together, from that perspective I mean, to design, formulate, and produce materials which, in the case of bone implants, promote the formation of new bone. We call those osteoconductive, and at the same time prevent the growth of pathogens. They are, of course, antimicrobial. These are some new ways that biomaterials scientists and engineers are thinking and they are exploring in designing the materials for implantable devices of the future. This is the end of lecture 22, entitled A Study Case Regarding Bacteria.